Hello? Okay. Can you hear me? Can you guys hear me back there? Can you hear me? I guess so. Can you guys hear me in the back? All right. All right, it's about 1:45. I'd like to go ahead and begin.
Okay, I'll go ahead and introduce if that's okay.
Oh, that's okay too.
Thank you for all attending our session today in this luxury suite meeting area. We're very privileged to have Alan Kukers with us today. Back in the 1st of September, Carmen Swamick, our chief structural engineer, sent me an email and asked if I could follow up on it by contacting Alan and talking to him about his presentation. And we discussed the fact that UDOT had constructed the first GRS bridge abutment project in the country on an interstate on I-84 near Echo. And he took the opportunity to describe some of the things that they've been involved with up in Idaho on their GRS bridge projects. So it sounded quite interesting for us, and I think we'll be well served today. Alan received a master's degree in structural engineering from Washington State University. It's not Weber State University, right?
It's Washington State, yeah.
Okay. WSU, I want to get that right, WSU. And has worked on several AE firms designing transportation structures over the last 20 years. He and his wife have 5 children, 2 of which are in college, 1 serving in the Navy, and 2 living at home with them in Idaho. And so thank you, Alan, for being with us today, driving down yesterday from Boise, and appreciate your time.
Thank you, and thank you for having me.
Yeah, we'll have a sign sheet here.
It was kind of interesting. I heard a little bit about, a little from the deputy director about how technology is changing. And one of the things that I'll be discussing today is, I would call it a new bridge technology, but physics doesn't change. How we use this technology does change. And one of the things about a year and a half ago, my supervisor came to me and said, "Hey, would you like to speak at a conference over in Idaho?" I said, "What do you want me to talk about?" He said, "How about GRS IBS?" And I had no idea what it was. So I looked online at FHWA's Everyday Counts and was able to put together a proposal and became the company expert just from that. And recently, we've designed the first GRS IBS bridge in the state of Idaho, and we're also designing the second. And it's kind of nice to hear that you guys have designed the first one on an interstate in the state of Utah. So I want to first of all ask, how many of you guys and gals have heard of GRS IBS? So everybody's really familiar? Okay. Not everybody. So what I'd like to do is I want to go over a little bit about the, bear with me. First of all, want to talk about what elements of the bridge the GRS IBS system is replacing. And I think it'd be good for those who are not familiar with GRS IBS to briefly, very quickly go through some of the elements of a bridge. And I'll kind of go through this quickly so that so those of you who are familiar won't get too bored with it. The GRS IBS system is the technology used to replace foundations, substructures, wing walls, and approach slabs. And we'll get into talking a little bit about what's so good about it. Trying to whet your appetite for it, for those who are not familiar with it. It's a really simple construction. It doesn't require specialized equipment. The duration for construction of a GRS IBS bridge can be on the order of weeks instead of months or years. It's very adaptable to field changes, and it's not sensitive to weather conditions. A lot of times we get caught up in meeting the winter requirements, well, freezing. Just bear with me just a minute. It's not sensitive to weather conditions. Like if you're doing concrete, you've got to deal with cold weather concreting, pouring in the winter. So it's not sensitive to that because you're using granular material that you're compacting as opposed to pouring concrete and placing steel. It gives good performance, and again, it's cost effective. One of the benefits about a GRS bridge is a typical bridge, a conventional bridge that we've had. At the abutments, what you end up with is usually a bump. And what's going on there is the superstructure and the substructure doesn't settle, but the roadway leading up to the bridge settles. And with that, you get this bump and also a joint that has to be maintained. And now you're looking at costs that your maintenance crew will incur. And if we can eliminate that, that would save more time and money to do maintenance on other things that other than joints and joint repairs, which can become costly. So looking at some of the documents that are out there, and a lot of these bridges were, there's on the order of hundreds of these bridges now in the United States, and they're typically 25% less than conventional construction, and that's kind of a generalization. There is a potential to go up to 60% savings if you self-perform. I'm dealing with a lot of counties that don't have a lot of money to replace all the bridges and do all the maintenance, and so these money comes at a premium. So they have a hard decision to make. What bridges are we going to repair, replace? And if they have a 5 to 6 man crew, they could potentially build their own bridge. But that also raises some other issues when you're doing self-performing work. You can hire someone to do it, and I'll show you a little later on one of the bridges we designed that even though it was sent out and a contractor is building it, I still think it was the least cost option instead of conventional concrete construction. And there will be variations depending on site conditions to the cost. In a nutshell, geosynthetic reinforced soil integrated bridge system. It's basically compacted granular material with a geosynthetic layer not greater than 12 inches. Typically, a lot of people have been using CMU blocks, and so their CMU blocks are 8 inches tall. So it's very common to have an 8-inch spacing. And the CMU block acts basically as a protection of the GRS fabric itself. And then the 4 bridge parts that I'd like to talk about real briefly are the foundation, the substructure, and I did not highlight the superstructure because the GRS IBS system doesn't replace this part, the approaches and the wing walls. So taking a look at, here's a typical single span bridge, a slight skew to it, and what we have as a superstructure would be the deck, as well as the beams, and in many cases, a voided slab, precast voided slab, is well suited for medium to short spans, and well suited for GRS IBS, and we'll get into that a little later. Then we have the foundation. In this case, the foundation is driven piles with a concrete abutment and wing walls. A little close-up of the detailing. And one thing I'd like to point out is if you look at a standard abutment, there's quite a lot of detail going on in here. And the detailing also shows you the complexity of the construction. Installation of the piles, the cage itself, the rebar, the formwork that is all involved, and then the delay for the curing time of the concrete before you set your beams. Then there's also the approach. In this example, we don't have what we call an approach panel or an approach slab. So right here's the superstructure, here's the pile cap, and then right in this area is your approach roadway. And this is usually where we end up with problems with joints separating, getting a crack or a bump at this location. And once that starts, it just exacerbates over time as you hit it with traffic continually. So this is a pile abutment bridge. And then another type of bridge would be a spread footing abutment. And again, pointing out the level of detail and complexity of construction for a reinforced abutment, concrete abutment. And this is a relatively tall wall, and now this has to act also as a retaining wall. And again, a little close-up of the level of detailing for traditional abutments. In this case, we have an approach slab, and what you've really done is shifted the bump to the end of the approach panel, because what you no longer have a bump here, which is great. You don't have to worry about as much joint damage or a bump here, but you still end up shifting the problem to the end of the approach slab. Again, just kind of a definition, excuse me. So just kind of recap on some of the parts of a GRS IBS system. It replaces traditional substructure and the foundation of a bridge. The foundation consists of a wrapped reinforced soil, and typically no greater than 12-inch lifts with reinforcement at 12 inches. And then you're stacking blocks, CMU blocks, vertically at the face. I'll show you a picture. Go ahead.
Could you just reiterate what the IBS part of the integrated bridge system, how that?
Okay, I'll do that on the next slide. Okay, so this particular slide came from FHWA's detailed drawings that they have on their website, and it's a great representation of what a typical GRS IBS bridge is. And here you can see the reinforced soil foundation, which is compacted granular material and is wrapped with a geosynthetic. And then this right here is the GRS. I would say this is the GRS area, the geosynthetic reinforced soil area, and it's broken up into sections in and of itself. There's components within it. And then the integrated bridge system, I like to think of it as everything above the bearing pads. So that would be basically your approach. It's reinforced soil, which replaces what an approach panel, a concrete approach panel. And basically this whole thing moves together. If you get settlement, the foundation, the wall, the bridge, the road, everything moves together. And so you're not going to get that bump. Now, you don't want a lot of movement. We're talking on the order of fractions of an inch, not inches. And also the wing walls I would consider part of the integrated bridge system. The wing walls being on the either side of the bridge, retaining soil, as well as restraining the superstructure transversely. And the next picture, I only show this because if we look at the previous slide, it's kind of busy. And I wanted to point out it's a pretty simple system. You just have granular material, a layer of geosynthetic, and a CMU block or a type of facing. There's a variety of facing materials that can be used. And then these are the different zones of a GRS IBS system. This area up here is what I consider the IBS area. So we have the reinforced soil foundation, which is not shown here. And within the GRS zone, We've got the bearing bed zone, the beam seat zone, acting much like what your beams would sit on a bearing pad or a pedestal, and it's about a 4-inch spacing, or even tighter, depending on the loads of reinforcement and granular. So you get a really tight layer right below the slab. And then we have the integrated bridge zone. This next slide, again, is a simplified graphic, just kind of showing the components. The spacing is a lot tighter, so you're coming up with 4-inch lifts of gravel. You can see here, the geosynthetic is just laid right on top of the block. A block is just stacked right on top of that. The fabric that is placed between the interfaces of the blocks just sits right up against the fill side of the CMU blocks. The other thing to note is your live load, dead load reactions is set back away from the wall. This prevents the wall from transverse or lateral movements, rather, just from the soil pressures building up. So that is one thing to consider, is the setback of your bearing. Some recommendations by FHWA, limiting the bearing pressure to 4,000 PSF, and I'll clarify what this means, because there was some misinterpretation of what this meant as we went through design. Heights are limited to 30 feet. Right now, I think 140 foot is the longest span bridge. And one thing that I think a lot of people are concerned about is the scour susceptibility of a GRS system. In Idaho, Idaho likes to drive H-piles, and so there was a little bit of a hurdle to work with ITD Bridge and getting them to feel comfortable with this particular technology. Just to reiterate, the bridge superstructure is sitting on top of a reinforced wall. The thing that makes this a little different than an MSC wall is the spacing of the reinforcement, and the behavior is different. Whereas an MSC wall, you're relying on the facing to hold the soil back. With this system, it's self-supporting because of the spacing of the geosynthetic. I'm going to run through a quick construction steps. The reason I'm going through all this preliminary is it kind of lays the groundwork for some of the things that we came up with, some hurdles or some things that we need to consider as we design the first GRS IBS bridge in Idaho. So that's the whole point of kind of sharing some of this foundational stuff. Real simple, not real complicated equipment. You're basically digging a hole. Notice it's being constructed in the wet. I want to note this is off the FHW EDC website. Once you have your hole, you lay your fabric, put in your gravel and compact it, and then it's important to level off the top of your reinforced soil foundation and lay the first course of blocks that it's square and level. Obviously, that's going to be your starting point. Now, I think you can use other products like a wire-faced wall, which would allow you a little bit of slop out in the field where you can, it's a little less, the tolerances for that are a lot greater. So there's a little wiggle room if you went with a wire-faced wall. But in essence, it's the same concept. Then you just start laying your blocks, placing gravel and compacting, and right after you compact, you lay your fabric. When you get to the top course, what holds these blocks in place are the weight of the blocks being stacked above. So everything's held in place by friction. So the top 3 or 4 courses, you'll need to grout and put in a vertical piece of rebar. And that's what this laborer is doing right now. He's grouting the top 3. And let me back up. One thing I neglected. The first 3 to 5 courses of block are solid CMU blocks. And as you get above that, you're using hollow CMU blocks, filling it with the same backfill material that you're using in the as fill material. And then when you get to the top 3 or 4 courses, you're grouting them and putting a steel rod through there. And then in terms of compaction, you're using a walk-behind plate compactor, which is very lightweight. You're not using a plate compactor or a roller compactor. If you look throughout these slides, the equipment is very, it's not complex equipment. Then you set your beams. In this case, these are voided slabs, or slab beams, precast. You set that right on the GRS fabric, and you'll notice there's a solid block. Actually, this is a solid block right here, and underneath it is a piece of styrofoam, polystyrene. And what that does is, as you set this down, this is going to be a stiffer material, being it's compacted granular material. And this styrofoam allows this block to deflect slightly, so you're not putting any load on the front face of your wall. And then this is the back side. That'll be this side right here. The ends of the beam. You lay your fabric, compact your gravel, and build it up. And now we're very near the level of the roadway. And at this point, you start building the wing walls. So about 3 years ago, FHWA had discussions with ITD Bridge, and they were very hesitant to even consider this technology. And what I found was there wasn't a really strong understanding between those who were presenting this emergent technology with the Bridge Group. And so the Bridge Group was very hesitant to start using this, especially on streams. One of the things, our local Highway Technical Assistance Council in Idaho, they are now mandating that all funds that come through the local highways take a look at GRS IBS, and with the hopes that this will provide more money for bridges that can't use this technology. And it isn't that we're going to use this for every bridge, but it's to provide more money for other bridges that can't use this technology. And there's a savings in money. And funding is, because funding availability has decreased, you know, the state is now considering more economical ways to, you know, build bridges. As Jim said, it's another tool in the toolbox. Some of the concerns that I came across as we were trying to implement this type of technology in Idaho was who designs the bridge, who takes ownership of the bridge. You know, like a Hilfiker wall, I've used those. I don't design a Hilfiker wall. Someone else seals it and stamps it. So that was a question. Who's gonna take responsibility for the design? What does this thing bear on? And how does the structure respond to just sitting on dirt? We have structural engineers are a little leery of setting beams directly on dirt or soils. So that was something that we need to consider. How do we protect the ends of the beams from corrosion? Scour protection. Right now, Idaho does not allow GRS IBS bridges on active streams, but for canals, local highways, we are using that. There was some question about bearing pressure computations. I mentioned that earlier, this 4,000 PSF. What does that mean? And that does have implications on how wide or how long your bearing area is, which relates back to how long your beams need to be. Then there's obviously long-term performance. You know, are there settlement issues, corrosion issues at the abutments? And then again, the application of this technology, can it be used in active streams? Ohio is using this technology on active streams. They have had floods on their bridges that have been overtopped with floodwaters, and they've seen no detriment to the structure. They're still functioning as designed. The other thing is local contractor familiarity. One concern is we put something out like this to bid. Are we going to get decent prices? There aren't any contractors in Idaho that have built this. And I would say that there's probably not a whole lot of contractors that have built this in the United States. And one particular person in eastern Idaho had asked me, okay, if we build it, then we're responsible for it. There's no warranty. So if you have a county or a city that decides to build it with their own crews, what's the warranty? Whereas if you have a contractor build it, there's usually a warranty. So that's something to consider. Talking with ITD and working with not just ITD, with the local Highway Technical Assistance Council, we felt that, no, we're going to take ownership of this design. So we will design it like we design any other substructure or foundation type. The structural engineer, it's a relatively easy design. I designed the wall system for a bridge that I'll be showing you. Pretty simple spreadsheet. You're looking at soil pressures, lateral pressures. However, you will need a geotechnical engineer to give you those parameters for the materials, friction angle, those types of things. Also checking for global stability. That's something that I wouldn't feel comfortable doing. I'd say a geotechnical engineer is the one to do that. The other thing is who seals the drawings. They wanted drawings that were sealed. They want a set of drawings that will be on file at ITD headquarters, not just a bunch of shop drawings for walls. In terms of the bearing surface, I think what works well for GRS IBS is a voided slab. You have a flat concrete surface. You don't have any cast-in-place concrete. You just set it right down on the fabric, and you're ready to go. If you have a steel structure, you're probably going to want to put down a concrete pad on top of your GRS. You might have to have a concrete diaphragm that basically gives continuity between the beams and allows the bridge to move on top of the GRS wall system. In our case, with a voided slab, we're using tie rods that just bolt through all the slabs, and they're tensioned. That holds the structure together. Typically, for a voided slab in Idaho, you have these tie rods just at midspan, and you end up pouring a concrete diaphragm on the ends. We've done that. We're doing that with a particular bridge with a high skew, and you'll see that in a minute. Also, how do you protect the ends of the beams, the pre-stressing? One detail that Idaho uses is a plastic sheeting that's basically glued to the end of the beams, and we can also glue this to the sides of the beams wherever there's earth touching the concrete. A little close-up of, this is our design of the Turner Penstock Bridge, and what you're seeing here is, here's the slab itself. If this was a square bridge, what I mean by that is it doesn't have a skew. We would have run threaded rods or rods through, or Dewey dags, through near the ends of the beams to cinch up all the beams together. But because of the 43-degree skew of these bridges, or this particular bridge, you're not really able to run a rod. You want these rods to pretty much go through perpendicular to the beam, not at an angle. And so what we decided to do with this bridge was to pour some concrete at the end of the beam and tie the bridge together in that manner. The only cast-in-place concrete on this bridge is the end diaphragm and a short, stubby wing wall. We're talking on the order of a couple of feet. The other thing we wanted to do was increase the concrete cover to the steel because it's sitting directly on a compacted material. In some instances, there's usually several rows of pre-stressing strands that you can put in a slab. We opted on this is another design. We opted not to use the lower level of strands, which is typically at 2 inches. We went up to the 4-inch and used strands to be placed just at that 4-inch mark to provide more concrete cover to the pre-stressing. If there are any questions, feel free to interrupt me and raise your hand. Scour protection, a lot of, Ohio and New York, I think Ohio especially, in some instances they are building these GRS walls behind an existing bridge abutment and leaving that abutment in place. This provides better scour protection. We were talking about this in our office for canals. If we can leave the abutment in place, there's less risk of creating a leak. So we leave the abutments in place, or cut them a little shorter, but leave the foundation in place. And then riprap is a pretty common protection for scour. Now we're looking at a bridge that we've designed in southeast Idaho. It's the Turner Penstock. And what we've done here is, here's an existing abutment that supports an arch plate, and we set the new abutment behind it, and we're leaving this in place. And the reason we're doing that is we didn't want to excavate this out and risk shifting the wooden penstock, which is used to provide generate power. And here's a detail of just the riprap in front of the abutment. Real quickly, if you go online, just type in FHWA EDC, you'll find some good resources there. One's a interim implementation guide, and they do have about 4 drawings on there that are a really good starting point. The bearing pressure, I talked to some folks at FHWA. This 4,000 pounds per square foot is not at the bearing of the abutment, not just below the beam. It's really basically at the foundation level. It's really to design global stability, not a localized effect. So you can get higher tire pressures. The performance to date, I think there's only, the oldest GRS IBS bridge I think is not more than 5 years old. It was the Bowman Bridge at Defiance County. Right now there still is no bump at the end of the beams. There is no cracking of the pavement. And the bridge is serving as it was when it was first constructed, as well as a conventional bridge, and perhaps better as there is no settlement. Here's a map. I think Utah now has a number 1 in that box. Idaho has a fraction. It's being built right now. So you can kind of see that this is a very new technology. A lot of it out here in Ohio and New York. What we found that was critical in delivering this project was understanding the materials you're using, how you specify the materials, how you detail it, and then also to have pre-bid meetings. If you want good bids, make sure that the contractors are well aware of the material availabilities, what's expected, and also that they understand the level of effort needed to build this type of bridge so they can put in a good bid, not feel like it's a big risk and they bump up their costs. We had 3 bids on Turner. And say again?
At the pre-bid meeting, what kind of questions or reactions did you get?
I don't think they asked a whole lot of questions. I wasn't at the pre-bid. Another bridge engineer was. But I think they all had an idea of how they were going to do it. But then after it was awarded, we started getting a lot of questions afterwards. And that's what you want to avoid. The typical facing material that's ideal would be a hollow block CMU. Even I can kind of grip it and lift it and place it. You can use modular blocks, a heavier block, something proprietary, but you do have to look at the geometry and how that's going to affect where the front face of your wall is. And again, gabion baskets can also be used. One thing we found out as we worked with this new technology was the CMU specs really aren't well suited for, well, let me back up. the GRS IBS specs for blocks were not well suited for standard CMU blocks. You can't go to Home Depot. Well, you could, but the intent is not to go to Home Depot and pick up CMU blocks and build a bridge. And the requirements that were a challenge to meet were the freeze thaw and absorption. And this is related to the durability of the structure. The other thing that was spec'd out in the interim specs was a 1/16 of an inch vertical tolerance for CMU blocks. And there are no CMU blocks currently spec'd for a 1/16 of an inch tolerance. It's an 1/8 inch. So I looked through the specs, and it's a dry stack spec. So if you're using mortar, you're going to make up that difference. We're not using mortar here. So we were able to, we felt that an 1/8 inch was adequate for construction. I met with fabricators. They're using, one particular fabricator said to make these CMU blocks meet spec, they could use their mixed design for modular blocks that met freeze thaw and absorption. Most blocks, CMU blocks that I've seen, are at 6%, slightly over 5%, and the interim specs are saying 5% or less. So with a modular block system, you are getting a 3% absorption and you are meeting freeze thaw. Basically, what you don't want to happen is you build your wall with these CMU blocks and all of a sudden the concrete is starting to pop off. And it's not a collapse issue, it's a durability issue. Just want to reiterate, the CMU blocks do not provide any support for the bridge. It's a facing material that protects the fabric and keeps the material from unraveling. You can use various types of geosynthetics. You can use a geogrid. What we found works well is a biaxial material, meaning you have strength in both directions. The reason being, if you have a wing wall that's close to your bearing, that wing wall also sees a lateral load. And for you to, if you can place a fabric in just one sheet without having to reorient it, that would be ideal. And so a biaxial material, so you're not having to reorient the direction of your fabric strength. It also, the geosynthetics do prevent migration of materials. One question that I was not expecting, and it came from an irrigation district, is how fire resistant are these geosynthetics? Because of the way they clean out their canals, you know, has anybody cleaned out a canal full of tumbleweeds? What do? They torch it, right? And so there was some concern about, is this going to melt? And you know, we talked to several people, and they said, no, this fabric doesn't melt. Matter of fact, when you build a wall, the way they trim it is to use a torch, and they'll trim out the fabric that's hanging out the front face of the blocks. This is very representative of the fabric that is being used currently for GRS IBS. It's called an HP series. I was fortunate enough to chat with the folks over here that are presenting their products. And here's something that is more expensive. You may need it if you go to taller walls and you need greater strength. Here's another type of product. And I'll just pass this around, get a sense of how stiff this material is, how a contractor might have to handle this. It's not like a bed sheet. It's pretty stiff. How are we doing for time? I'm going to have to blaze through this pretty quick here. So the things that we found that were important were things that we need to consider in detailing is what we don't want to do is have a contractor go out there and not really know how to build it. Not have any idea of, you know, how are they going to start this. And so much like any other bridge, we have a foundation layout, we'll have a wing wall layout, and the other things that, you know, instead of having rebar, now we have reinforcement, fabric reinforcement. So we also need to think about how are they going to lay out all this fabric. You know, this is quite a large area when you start laying out the fabric. What elevation will it be at? How do you cut it? And also, how are they connected to the walls, the block walls? And also guardrail installation. Can you drive the guardrail off the bridge in through the fabric? What's the setback to the blocks so that when you drive your guardrail post, your blocks aren't moving? Communication is going to be critical between, these key players, the owner, contractors, fabricators, the engineers. I think pre-bid meetings are really key. Dialogue even before these things come out. So getting to Turner Road, Pacific Core penstock, I call this the 10-foot diameter wooden soaker hose. I suspect that a lot of these have 22 caliber holes in it from kids. It's out in farmland. Turner Road has been closed for 2 years. It's a farm-to-market road, and the local community has really been wanting this particular bridge, this road open, because they have to take about a 5-mile detour to get their agricultural products out. It's in southeast Idaho. It's a 2-span steel arch, and believe it or not, this is a historic structure. And we found no steel, no reinforcement in this concrete head wall. You can see that it's starting to separate here. There was fill material coming out here, so a steel plate was driven between the wall and the fill material to keep it from spilling out. And I think this ladder might be holding up this wall. Has very shallow bedrock. What's interesting about this is on the west side of the bridge, the bedrock is about 10 feet below the bottom of this ditch. And on this side of the bridge, it's right at the surface. You can see here, the bridge that we're putting in is a very aggressive skew, 43 degree skew. This creates some additional challenges, but what you'll see is even with the challenges, a GRS IBS bridge can be used to accommodate complex geometry. The first thing we looked at was a foundation plan. We did not use a reinforced soil foundation for this particular bridge. We used a controlled density fill, which is a very lean mix of concrete. Some people call it flow fill. The reason we used it here was the constructability, as well as it reduced the amount of geosynthetic we needed for this project, and it was related to global stability for this particular site. What it also shows is you're not locked into using an RSF, a reinforced soil foundation. You can still pour some concrete and still build the wall up using blocks and reinforcement. On this side of the bridge, we just had a leveling pad because the basalt is very near the surface. This just shows you a little bit of the level of detailing that we went through to produce this set of plans. Typical like any other bridge, there's an abutment layout, a front face. I think many of you have done retaining walls using block walls, very similar, put in alignment for the wall face. This bridge had some challenging geometry because of the skew. We had a bend in the wall. Close-up of the detailing. Because of the skew of the bridge, let's see if I can show this. So what we have here are, I believe, 7 voided slabs that make this trapezoidal shape. Typically, you run a steel rod through all of the beams and cinch it. We couldn't do that at an angle, and we didn't want to put in a series of stepped bars. And so what we did for this instance, I mentioned this earlier, is we poured a concrete diaphragm at the end of the beam. And the other thing about skewed bridges, as the bridge expands and contracts, you don't want to develop pressures behind the bridge itself. How many have done a skewed bridge? Okay, what happens is the bridge can rotate or rack, and this particular bridge is just sitting on the top of an MSE, well, a GRS wall. That was a slip. And so we wanted to minimize the pressure that could build up behind the wall. So we built a little CMU back wall to provide a little joint, a gap between the bridge and the soil. The other thing we did is, I can't zoom in, we have this GRS, or we have this geosynthetic that is at this level right here, and we also need to pour grout and place a steel rod down that cell, that hollow. We were concerned about the lack of contact space between the geosynthetic and the blocks. So we basically detailed cutting the fabric, 3 sides of the fabric, and then folding down a flap into the cell, and then you can pour the grout down in there. And that you do that with the top 3 to 4 courses of blocks. This is a layout, the fabric layout. You want your fabric to be at the same elevation for every course. And so we detailed different sections in plan view of how the fabric is laid out at the various zones to help the contractor visualize how the fabric is laid out. And you can see here, these are the wing walls, and there's a little more complexity here. We added a stubby wing wall here to provide transverse resistance, so the bridge had something to bear up against to keep it from moving. Closer details of the wing wall area, and what you see here is the placement of the guardrail posts off the bridge, and what we've detailed are locations of the guardrail posts, and we recommended for this bridge that fabric be pre-cut for the post holes, so when they do drive it, you're not pulling on the exterior wall blocks at the top of the GRS IBS. We accommodated the cross slope, the crown of the bridge, by putting a crown into the GRS IBS GRS fabric and granular material right below the beam seat. So here's where the beam sits, and so this is a variable depth that gives you the crown of the road. That way your beams are laid at a 2% and a 2%. If we have a center beam, sometimes we'll have a 2% crown cast into the beam. A much simpler bridge that we're designing now is in Jerome, Idaho. It's a small canal bridge. This bridge is just under 20 feet, and we're designing it as a 50-foot span, and you'll see why on the next slide. So this yellow area is how long the bridge is and how wide the canal is. You can see how it's choked down. And so what we've done is we've lengthened the bridge out to accommodate what's out there hydraulically. Again, now with this particular bridge, we have no skew. And so I was talking about that steel rod that we cinch these beams together with. So we have one at midspan, and we have one at each abutment to hold the structure together. And these beams are also grouted, and there's weldments at the seams. Plan view, much simpler foundation plan compared to the other bridge, which had a skew. Here's the existing abutment. We're leaving those in place. This is a canal, so we wanted the least amount of excavation. So our bridge will be back here, and it'll span over the existing abutment, and we'll partial demolition of the existing abutments. These are similar details. We used a lot of the details from the previous bridge we designed and modified them to suit this particular project. With this bridge, we don't have any concrete diaphragm. We just have a steel rod that runs between the slabs. Because we don't have a diaphragm or stubby wing wall to provide transverse resistance for movement, we decided to put in a 3-inch diameter pipe with a pointed tip driven through a hole in the precast beam to provide the restraint of the abutment, of the bridge rather. Same type of detailing. Plan view of the wall layout. We need to lengthen one section of the wall. We have, for this particular bridge, we will be using the reinforced soil foundation instead of the controlled density fill. These drawings aren't complete yet, but we'll also have an RSF at this upper level. So what you're seeing here is a stepped wall. This is the wing wall. Abutment details. The key here is to ensure you have the elevations called out so the walls are built to the correct elevation. And the way we are accommodating the crown of the road, we're keeping the blocks all level, and then we're adjusting the granular material, the layer thicknesses from the edge of the deck out to the center of the bridge to make up that crown. Some more details of what the wing walls look like. We have this set back quite a ways from the guardrail. This one won't need holes in the fabric. There's enough distance that driving this through the fabric won't be an issue. So real quickly in summary, know your materials. I think communicating with the fabricators, with the owner, with the contractor, have clear drawings and clear specifications. One thing I forgot to mention is the type of material you call out for backfill. You can have an open graded material or a well graded material. On our Turner Road Bridge, we called out a well graded material, and you can check the density and the compaction with a nuclear densometer. The contractor opted to use a open graded material, and you can't check that with the nuclear densometer. So we had to come up with more of a performance criteria for how the open graded material would be compacted. And then there's the FHWA Everyday Counts as a resource. On the second bridge that I showed you, the square bridge, the S Canal Bridge, I've spent about 40 hours of my design time. Well, actually, I didn't do any design, really, on that at this point. In terms of design effort, it'll be about 20 hours. Most of what was done was geometry. The geotechnical engineer did much of the design work. Most of my work is geometry, and we had a good CAD tech that put the plan set together. It is designed. Most of my time, again, was in meetings, coordination, and so you also do save time in design effort. Any questions? Yes?
Comment from the geotechnical effort, it should be noted that the FHWA docs and the FHWA resources, they actually include now a seismic design guide. It's very important to take a look at, particularly when the accelerations and ground accelerations get up a little bit high enough where you need to be concerned about how it's going to be reacting.
So the comment was FHWA now has seismic design criteria for GRS IBS. Fortunately for the bridges we're doing, we're low seismic. However, there is still, you need to design the connection at the abutments. And I can't remember what it used to be, 20% of the dead load. That's now since changed in terms of what the connection forces should be. And that's something that we're designing into the abutments. Did you have a question over there?
Yes. The question I have is the Reinforced Earth Company has been designing true abutments for over 40 years that service since 1974 in Nevada, which is a non-pile supported abutment. So my first question is, what is the cost benefit of the GRS IBS system versus a traditional MSE wall?
I think that's where you'll have to look at, in terms of cost, well, they're two different things. If an MSE wall behaves differently than a GRS IBS system, I think the big benefits are self-performing in terms of lightweight. The materials are typically lighter to lift, whereas if you have a MSE panel, I think you're going to need, it's a little more cumbersome to handle that. Typical lifts are 2-foot lifts for MSE walls, I think. In terms of price, I think if it goes out to bid and a contractor builds it, I think they would be comparable. I don't think we have enough historical data out west as we do, in the eastern part of the states. One thing I did hear mentioned by a contractor, I don't know if it was a contractor, they talk about labor costs and how it might be that we have higher labor costs over here than on the east. And if they're self-performing, they can, maybe it was the other way around. I think you do have to look at the labor cost. I don't have a good number for how well I don't have a number at all, how they compare.
And another question I had is, I saw a lot of everything is FHWA, which is Federal Highway, and typically in DOT projects, AASHTO is the governing code. So how do you specify design code?
We are using AASHTO loads, and in terms of an MSE, like AASHTO does talk about MSE walls right now, but it does not address GRS IBS. And I think that's where working with, and that was a concern that ITD had, is this an AASHTO design? That's a good comment.
And then the question I have is, from the drawings I've seen on the GRS, you have 4-inch lift thicknesses. So how do you really get a good nuclear density with only a 4-inch depth?
Okay, so the GRS IBS is 12 inches maximum lifts. So when you get to the very top, now you're getting into the 4 inches. That I don't know.
So I guess one of the other questions that was just brought up was the seismic, and with the traditional MSE wall, you have a mechanical connection versus with the GRS as currently designed, it is basically a bearing connection. So is it suitable for seismic right now, or does it have to be redesigned prior to the use of GRS in a seismic zone?
From the literature I've read, I think the GRS IBS, I think they have done shake tests up to 1G, is what I recall. In a high seismic zone, there are probably going to be some other issues that do need to be addressed. And so this is not a one-shoe-fits-all. Okay, it has its place. It's just one other bridge type. And I think those are things that need to be considered before and should be addressed before selecting this for a particular site. Right now, I think a lot of clients feel good for low seismic zones, non-active streams. So it's like baby steps for some owners. They're not just going to jump right in and say, we're using this for all applications.
Correct. I understand that point. My question was with the cost of it, pretty much, because there's a big push to utilize it. But if you think about the constructability of it, moving backfill and placing backfill, they're not using wheelbarrows and shovels, but they're using the same equipment that you would to build an MSE wall. So that's my question on the true labor savings. If you have additional lifts of the soil reinforcement to place every 12 inches compared to 30 inches in a traditional MSE wall.
The costs may be comparable. I'm not saying we just don't have the cost. I don't think we have enough cost data right now to say a GRS IBS wall is going to be cheaper than an MSE wall. It is a technology. If it's a different tool, it can be used. And I think you do have to take a look at the costs for both. I don't think you want to eliminate an MSE wall, a traditional MSE wall, and just go straight to GRS. It's a lot like doing a TSNL report. You're going to look at different types of bridges. So you're going to look at different types of substructure, whether it's an MSE wall, a Hilfiker wall, or a GRS IBS wall. So I'm not saying that this is for everything. Yes?
I'll comment that our contractor from Dry Creek Structures on our I-84 GRS bridge said he saved about $1 million on that project over the $6 million bridge project. So we thought that's considerable. That's not quite 25%, but that's still a pretty big savings.
You want to repeat? Okay. What project was that?
Our I-84 ECHO project,
The I-84 ECHO project saved, was it $1 million?
$1 million out of 6.
Out of $6 million using GRS IBS. I think there's cost savings to be had. It's an emerging technology. I think this type of discussion is important, where we do raise the concerns of this particular technology, what's its application, and these are the things that I was trying to communicate between FHWA and with ITD Bridge, so that we're all on the same page, and that there's no miscommunication about, oh, this is going to meet all your bridge needs, and that's not what we're saying. But it is definitely a cost-saving, I think, a cost-saving technology.
Jim, what were your decisions based on the question of seismic performance on an MSE wall versus a GRS wall?
I've been involved in the 3 InSharp studies on GRS bridges, and the second study, like he noted, involved large shake table testing. And he was correct in saying that we shook it on 4 different accelerations up to 1.0 G. At the 1.0 G shake table test, they had a little bit of deformation on the blocks, but there's no structural integrity problems at all.
This on the GRS.
On our GRS test study, on the second InSharp study. The results of that can be found on Federal Highway's web-only document 187 for those results. Right now we have the InSharp study going on now, and that is also considering seismic, and that is going to try to promote an actual accepted methodology for GRS, which, like he's discussed, doesn't involve the same methodology that AASHTO uses for MSE wall. It's not a tieback system where an MSE wall draws all this load to the wall face, and you have to have this positive connection. With GRS, you don't have to have that. It's a soil confinement type situation, and that's what our InSharp study is trying to tackle. We're having a real good research team headed up by the University of Texas, Austin, and we're expecting some good results from them that might get towards AASHTO certification, the T15 committee.
So to follow up, so you're comfortable with that?
Yes, we are.
So the second is AASHTO is following that bid process.
We hope.
Notifying.
We hope. There's no guarantee, but that's our goal for InSharp study.
Thank you for your attention.
Thank you. The roll, make it all the way around. Anybody not get the roll?